Now let's look at some further examples of the application of Newton's second law involving rotation, involving circular motion. In this case, what we have here is a rigid rod that can move frictionlessly about that point. It can rotate frictionlessly about that point. We're given the fact that the lower end of the rod is moving horizontally at a given speed of VA. Okay, and the rod is momentarily vertical. The mass of the rod is M, and the length is L, and the mass is uniformly distributed. Okay, what I want to know is, at this moment, given that speed VA, can I find the tension in the rod anywhere? You know, the tension varies, right? You can expect that at the top here, you have the greatest tension because to support all the weight of the rod, plus it has to support the movement of the rod. At the bottom here, point A, the tension is 0 because it's not supporting anything. Okay, so the tension should be variable. Let's establish a coordinate system like this. We call it the x-axis. Okay, so obviously T, the tension will be a function of x. How do you figure out the tension? It's a variable force. And also, if you look at different points on this rod, they also have different linear acceleration. This point does not accelerate at all. This point has a certain acceleration, but not as large as that, because, you know, it's further away with a greater speed. Let us look at, therefore, a certain small portion of the rod. The reason why I want to do that is because I can only apply Newton's second law to a system with a uniform acceleration throughout its entire body. This object from here to there does not have the same acceleration between this point and that point. So that, therefore, I must imagine cutting into small pieces and study Newton's second law for each little piece, because for that little piece we know the acceleration is more or less the same throughout. Okay, so let's look at this little piece here between x and x plus dx. This is something we've never done before. That is, taking an object apart, looking at an infinitesimally small portion of it, and applying Newton's second law to it. Again, this is necessary because of the non-uniformity of the acceleration throughout it. Okay, so this is our system now. It's a tiny little piece. Let me isolate it out. It's a tiny little piece. Okay, and let me draw a free body diagram on it. You have tension, right? I'm sorry. First of all, let's do the standard thing. Let's first find the non-contact force. That's gravity going down like this, mg. It's actually the mass is dm. It's because it's a tiny piece times g. Right? That is gravitational force. What else do we have? We have tension, right? Tension. It's being pulled both ways by the rest of the rod. That's tension. It is being pulled upward by a tension T. That is at location x, right? Because that coordinate is x. Here's x plus dx. At x plus dx, the rest of the rod also pulls this piece down. That tension is T of x plus dt. I can also write it as T at x plus dx. It's the same thing. T at x plus dx, I call it Tx plus dt. So there's a difference in the tension here. Here's T plus dt. These are the three forces, 2 contact force and 1 non-contact force. So what I'm going to do next is to use Newton's second law to study the motion of this little piece. What is the acceleration of this little piece? Well, see, it is going this way about a circle centered right here. The radius is what? Is x, isn't it? The radius is x. So what is the acceleration now? The acceleration A for this little piece is equal to Vx squared over x. What's Vx? Vx is the speed of this little piece. Now remember, the speed is V sub A at the tip. This distance is L. From here to there is L. How fast is it moving here? What is V of x? Well, they turn around by the same angle, so the only difference is between V and VA is due to the length, radius. One is x, the other is L. So V of x over VA, that should be equal to x over L. This is x, this is L, right? This proportionality. So I know what V sub x is. That is just VA, which is a given constant, times x over L. So I can write this as VA squared over x, then times x over L squared. Okay, that is the acceleration. So I know the acceleration, which is this way, which is actually, it moves this way. Okay, it moves this way. The acceleration points toward the center of the circle. You know, the acceleration is like this, right? It points toward the center of the circle. So this is the direction of the acceleration. Let me choose this direction as positive then, because it points toward the direction of the acceleration. So the net force along the positive direction would be equal to T of x, that's positive, minus dm times g, that's down, then minus this guy, right, which is also negative. This guy is T of x plus dt. So what's the net? You see, tx and tx nicely cancel. You get negative dm times g, then minus dt. Okay, minus dt. What is dm? dm is the mass of this little piece. It is a portion of the total mass, and since the mass is uniformly distributed, dm depends on how thick it is from here to there. The thickness, of course, is from here to there. That's dx. So isn't it true that dm over the total mass should be equal to dx over the total length L? L. Same as this L. So I know what dm is. dm is dx times m over L. Okay, so that's dm. It is negative dx over L times mg, and then minus dt. That's the net force. But what is that equal to? Isn't that equal to mass times acceleration? Mass is, mass is dm, right? Mass is dm, which I know. It is dm times a, which is equal to, dm is right here, m over L dx. A is right here. A is right here. I have to plug in the value for a now, which is, I'm just copying this, okay? VA squared x over L squared. I'm just solving it. X squared over x, then divided by L squared. So I have an equation of motion now. On this side, I have this. On the other side, I have that. Let me simplify them, okay? I'm going to write it down clearly, and then I'm going to simplify them. So I have negative dx over L mg minus dt equals m over, I'm just copying everything, m VA squared L to the power 3 x dx. All right? Now, exactly what I'm looking for. I am looking for t. How it depends on x. I only have dt. So let me solve for dt and I can integrate. Okay, let me solve for dt and integrate. So what's dt equal to? dt equals to, move this dt to the other side. You have two negative terms, one here, one from there. Negative, everything has m over L and dx. So I'm going to take that out, m over L. And you have, here you just have g plus VA squared x over L squared, and then dx. Okay, this is just rearranging the terms. What do I do next? I want t, not dt. So let me integrate. Okay, let me integrate from one end of the rod to the other end. Okay, let's look at the range of integration now. You go from here to there. This is the origin, okay, where x equals 0. And you go all the way to x equals L at the other end. Meanwhile, what happened to t? You have t here, you have t there, right? Well, actually, if I'm looking for t at any arbitrary location, I don't want to start from all the way from here to there, that would mean that from that I can only get t at this point versus t at that point. If I want an arbitrary location, what am I going to do? Well, then I can start from here to an arbitrary location. I can integrate like that. But the problem with that is that I don't know exactly what's the tension at the very top. Okay, now what I do know is that tension here has to be equal to 0 because, you know, right at the edge you're not supporting anything. Okay, the mass of the edge is 0. So why don't I integrate from a certain location x all the way down to here, x equal to L, because I know exactly what happens at that point. That's t equal to 0. So upper limit is x, lower limit is x, upper limit is L. Okay, so I integrate from x to L. Meanwhile, this is the starting point, this is the end point, right? At the starting point, the tension is T at x. End point is tension at A, which is 0. Right? Okay, we're now ready to finish this integration. This side, 0 minus Tx. The other side, let's work it out. Negative mg over L. Okay. And then you just integrate over dx, so the answer is L minus x. Right? And then the next term, minus m VA squared divided by L to the power 3, taking all these constants out. What's left is x dx. You integrate, that's 1/2 x squared. X has to go from x to L. Okay, this would be, when you plug in the lower and upper limits, you get L squared minus x squared, right? And there's a negative sign, so you solve for t of x. Let's look at the final answer. Okay, here comes the final answer. The tension at distance x below the supporting point equals the sum of two terms. Let's see if these two terms make sense. What's the first term? It's mg times L minus x over L. This obviously is due to the weight that you have to support. In fact, let's see, it actually makes perfect sense. You look at the tension here, right? This tension, even when the rod is not moving, this tension at least has to come up with enough force to support the weight from here to there. What's the weight from here to there? It's the mass from here to there times the acceleration gravity. Now the total mass is m from here to there. What fraction of mass is contained between here to there? That's the length from here to there over the total length. The length from here to there is L minus x, because this is x. So this from here to there is L minus x. Divided by the total length, that gives you the fraction of the mass between here and there. So the mass between here and there is m times L minus x over L, right? And then times g. So the first term is clear. The physical nature of the first term is clear. It's just the weight you have to support. But in addition to that, there is a second term. Here's the second term. What is the meaning of this term? Well, this term you see is proportional to VA squared. What's VA? VA is the velocity at the bottom. You see, the reason why we have this second term, is because the tension is not only responsible to support the weight, but also as the thing swings with a velocity, it is doing circular motion. Different parts of the rod is doing circular motion at various radius. And for circular motion, all these different points have the same center, which is right here, which means there has to be a centripetal force pointing toward the center of the circle, which exceeds the weight. Okay? If the force tension equals to the weight only, then you're not going to be able to do circular motion. It just dangles without any motion. If you're doing a circular motion, we must have an upward force in excess of the downward gravitational force. And that happens right here. In fact, if you set V equal to 0, the second term disappears. All you have to support is the weight. Okay, so what did we learn in this problem? We learned that in some cases, you must take a whole object and break it into small pieces because various points on that object have different acceleration. So we must isolate one little piece out because only this little piece has the same acceleration throughout